Hello, everyone. Welcome to today's SMaRT seminar. We have another wonderful talk today. Uh, Today, it's my pleasure to introduce Dr. Youngsoo Choi, who is a chief scientist in the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. Dr. Choi develops scalable and reusable learning frameworks to accelerate scientific simulations with contributions spanning in the domains of reduced order modeling, data-driven surrogates, inverse problems, and uncertainty quantification. He leads the LibROM team and has been instrumental in advancing open source tools that bridge computational science and machine learning. Now, with that brief introduction, please join me in welcoming him for today's seminar. Thank you. It's all
Thank,
yours, Yanshu.
thank you. Thank you for the nice introduction and for the invitations. I'm really honored to be here and get to talk about this exciting topic to you guys. So today I am going to talk about foundation models for computational science. And as you know, foundation model is a hot topic these days. Um, Pretty much everyone is talking about it. You know, thanks to the ChatGPT and Gemini and Anthropic's Cloud and many others. It's literally changing our daily lives. There are, because of those big impacts, the folks in computational science, it's very natural to bring those powerful concept of the foundation model into the computational science. And there are many existing foundation models in computational science. But today, I'm going to introduce another foundation model in computational science, you know, probably somewhat different from other existing foundation models in a way that ours will incorporate the physics and tightly integrate it into our model. And then also in the beginning, I will go over how we can properly define and desirable characteristics of the foundation models in computational science, because in our perspective, there is a concept called the foundational method in computational science already, like the finite element method and finite difference method and finite volume method. And those concepts, the existing foundational method, we should be able to use, you know, you know, their characteristics and why they are called foundationals, etc., to define properly the real concept, real definitions of the foundation models for computational science. Okay, it's too much introductions. Before I delve into it, let me recognize our awesome collaborators. Without them, nothing would have been possible. So I was so fortunate to, work with them on this exciting topic. Okay, as I said, there are many foundation, many models which are claimed to be foundation models, and one of the misconception would be, the neural surrogates. A lot of people calling it foundation models. I don't think it is foundation models because a lot of times this neural surrogate model is trained with some specific input geometry boundary conditions using simulation data, sometimes from experimental data or measurement data, and in supervised or unsupervised manner, trains some sort of neural net, and it can predict the outputs. However, a lot of times it does a good job in the training domain, like, that in other words, like the interpolation regimes. But if we ask to predict the outside of the domain, outside of the distributions, then it does quite poorly. It is because it's learning the map, not particularly a internal structure or intrinsic structure of the physical systems you're supposed to learn. So definitely these many neural surrogate models are not foundation models. There are models which learns the structure, right, in intrinsic structure, like the neural operators, and try to learn the functional operators like the FNO or DeepNet. And there are other neural surrogates which does a better job on the generalizations in terms of the geometry, the scale up and the changing the boundary conditions and initial condition, etc., like the transformers and graph neural network. So many existing foundation models are based on these models, like the transformers, GNN, FNO, and DeepNets. And the way it is trained is similar. It uses the data a lot of times, and once it is trained, it can predict the new outputs. But because we are dealing with the computational science, such as like 5D turbulence on tokamak devices, which is very, very complex. So, you know, in order to, fine tune the transformers GNN and FNO DeepNet to make a good prediction for this 5D turbulence on tokamak device, perhaps your models were trained on some other physical systems like Navier-Stokes, the pure just traditional the CFD with the simulations, and trying to extend that to the 5D turbulence on tokamak device with this complex geometry. um, it's hard. So basically, this fine tuning is going to be very expensive. Pretty much you have to retrain and takes hours and hours of retraining. And if that fine tuning takes that long time, then it's not practical foundation models, right? And it's not because those models are bad, but it's because very special characteristics, some challenges we have to deal with within the computational science. Um, you know, dealing with this kind of challenging of expensive fine tuning. And later in the presentations, I'm going to lay out what other challenges are there. But basically the computational science, the building the foundation model is very very challenging task. Okay, so let's go over the concept and definition of the foundation model in usual AI sense. As I said before, BERT, GPT-3, and CLIP, some vision models are called the foundation models. Uh, um, and the folks from the Stanford, they came up with this definition um, to capture these emerging behavior of the foundation models captured by the large language models and vision models. And they define it as any model that is trained on broad data, generally using self-supervisioned at scale, that can be adapted to, a wide range of downstream tasks. For example, wide data, they use text and images, speeches, structured data, and 3D signals. And once those model is trained, and it should be able to, uh, handle, without like expensive fine tuning, like such as questioning, answering, sentiment analysis, information extraction, image captioning, object recognitions, and instruction following, etc., etc. So the key here is, does the foundation model has a like broad generalization capability, and can you do that without expensive fine tuning, and can you do that with like the broad data set, right? So let's keep that in mind. Those are the characteristics we would want from AI perspective, for the as a quality of the as a characteristic of the foundation models. Now let's go over, some of the foundational methods in computational science, because in computational science, we already have the concept called the foundational methods, like the finite element method, finite volume method, which usually a very powerful tool for fluid simulations, and finite difference method or spectral method, and many others. These methods are called foundational because they have features such as universality and the mathematical rigor and the software reusability. Okay, let's go over universality first. The method such as the finite element method, it has a general strategy which doesn't change as you change the problem. For FEM, like you form a weak form of corresponding, governing equations, you discretize them, and then you solve for you introduce some basis functions, and you solve for the unknown coefficient in front of the basis functions in numerical way. That fundamental framework doesn't change; it stays the same. And only thing you need to do to solve a different types of problem, you change the inputs and material properties and boundary conditions, etc. It's universally those framework is universal. How about the mathematical rigor? Thanks to the great mathematicians such as Hilbert, Courant, and John von Neumann, these and many others, and these methods are supported by a mature mathematical theory, like the concepts like convergence, stability, and error analysis are well defined and studied, as we all know. And this, mathematical rigor is the reason, one of the strong reasons why, those methods are called the foundational in computational science, because it guides us and make the methods robust, so that it can be applicable to many different problems. How about the software reusability? I mean, these methods, once it is implemented, you don't have to rewrite any routines from scratch. You can build up, and you just need to change the input files, and it's basically applicable to many different problems. So let's also keep that in mind. These are the characteristics, of the foundational methods which already exist in computational science. And now, with those characteristics, let's try to define properly what the definitions of the foundation model should be for computational science. Our group has come up with these definitions, and here we go. The foundation model in computational science is a data-driven model trained on a broad distribution of scientific application types or physical systems, which exhibits wide generalization capability across scientific problems, computational domains, tasks, and physical condition, without requiring the retraining from scratch or structural modification, and serves as a reusable base. Okay, as you can see, we try to adapt it many some of the characteristics we have went over for the foundation model in AI's perspective and the computational side perspective. Let's try to dissect that one by one. So first of all, it's gotta be data driven. Otherwise, in AI sense, it cannot be foundation models, right? I mean, those FEM and finite volume methods are not foundation models in AI sense because they are not using data. And when you use the data, you gotta use a broad data set. In computational science sense, it could be maybe a Stokes data, Maxwell, wave, transport, Poisson, Burgers, elasticities, and many others, right? Basically, you use those data, the broad data set. And once that model is trained, just as a desirable characteristics from AI and computational science, both fields, it's gotta be generalizable. It should be able to tackle many different boundary conditions and for many different parameter inputs, and not only the forward simulations, but also inverse problems. Not only the single physics, but the multi-physics problems, many different equations. A lot of times the governing equations is described by the partial differential equations. Yeah, all these different partial differential equations should be able to be handled by this single trained the foundation models. And for many different geometry, right? I mean, it could be rectangular, circular, or star shape, or 2D, 3D. And if you go to fusion, kinetic equations, regimes, you should be able to handle 4D, 5D, 6D, and 7D, like the high dimensional, the equations as well. And not only the deterministic problem, also the uncertainty quantification problems, and it should basically scale up as you add more data. So, and you should be able to do so pretty much with almost no retraining from scratch, or if you have to do the retraining or fine tuning, some sort of adaptations, then that adaptation fine tuning procedure has to be very, very fast. And, another words of the generalization capability, yes, you should be able to reuse those pre-trained model for many different tasks. Okay, and we do have some additional desirable characteristics to be foundation models in computational science, and it's because of we are dealing with the computational science, and it's one additional desirable characteristic is scientific consistency. A lot of times, domain scientists, they require the solutions to be also physically consistent, like a lot of first principles it must satisfy as a predictions, as a physics, the foundation models. It should satisfy a lot of structures like energy conservation, momentum, the mass, and some system has to be symmetric, and some field it shouldn't be negative. It's gotta be strictly positive or non-zero. And all those things, additional constraints, if the foundation model does not give those kind of outputs, if it's just looking good in eyeball norm, it's not enough. Like the domain scientists, like the chemistry physicists, and they will not be happy with that foundation models. Also, just like the finite element methods, finite volume methods, those existing foundational methods in computational science should be guided by mathematical rigor. And robust extrapolations and data scalability are natural, the desirable characteristics. As you increase the data, your model should be, should improve. I mean, that's how, like the ChatGPT or many other Lawrence, the large language models, how they improve it, right? They add more data, or they increase the model size, and the performance gets better and better. That's how they advance the version of the ChatGPT, for example, from 3 to 4 to 5, etc. Okay, so having said that, these are the definitions and desirable characteristics which supposed to have as a foundation model in computational science. You may ask, is this foundation model even realizable? Can you even actually build such a model that satisfies all these criteria? Uh, it sounds impossible if you understand how the computational science works. Um, it's because there are so many challenges to block and those foundation models to satisfy those kind of characteristics. So what are those challenges? It's very important to understand what are those challenges. The first challenge would be massive data point size. So I gave you this example before, the 5D turbulence on the tokamak device. It's just single data points, like one instance of the simulation case. Its data size is like, involves a millions or trillions of values, unlike the other foundation model, like the application area, like natural language processing or vision, where the single scientific data is a very small, like the tokens and the word, and which probably the size of the data is bytes and not even megabytes. Um, this the data single data size from the computational science, like the 5D turbulence model, its data size is humongous. It could be gigabytes or terabytes, and very easily, just for the single point. But to enable the foundation models, we gotta generate big data, right? A broad set, not just the big data, broad set of the data. So it seems almost impossible to handle, this single data size being, gigabytes and terabytes, and you need to generate millions of more data sets. It's almost sounds impossible to build a foundation model for that. And because of that, it, it's unavoidable to go through the expensive fine tuning, right? Let's say you pre-train the model using this, fluid dynamics data, and you try to, um, you know, adapt those, pre-trained model for the solid mechanics problem with a very different geometries and meshes, and naturally expensive fine tuning is required, and that's definitely a challenge. And data heterogeneity. Some model deals with the scalar values like the temperature, field, or the vector values, just like the velocities and etc. And some data types might be matrices, like 2D, the dimensional, the matrices, or if it could be even tensor. So depending on the applications, your foundation model should be able to handle the 1D, 2D, 3D, and even multi-dimensional the data types, which definitely adds the challenge of building the foundation models. And the lack of the standardized data sets. Unlike the large language models, it's hard to come up with a standardized data sets. I mean, there are groups of people out there, like the Well and the PD bench. They made the data available through repositories and try to make those data as broad as possible. They did a pretty good job. However, um, even those data sets are not enough, right? I mean, we need a lot more broader data sets, and also a lot of times, each groups in worldwide, those computational science research group, they tends to have their own, way of generating the data, and those data types, although they are solving the same problem, a lot of times they don't match. And coming up with a standardized data sets, and which can be shareable globally, so that the people can use the same data set and come up with a, their own model and compare those models in fair manner, it's basically pretty hard things to do. And mesh and geometry dependencies, like some mesh is structural mesh and unstructured mesh, or some are requiring the adaptive mesh refinement, and some has mixed like the structure and unstructured mesh in embedded manner. And all those, different types of meshing also add the challenges. And how about like the physics-informed constraints, like the scientific consistency? As I mentioned, it's really hard, for example, for the neural surrogates or black box approaches to come up with a, physically consistent and healthy the outcomes. How about the interpretability? Like the neural nets, it's relatively new compared to the differential equations. Differential equations, we know a lot about them thanks to the great mathematicians starting from Isaac Newton. And so we can interpret them very well. However, the neural net, once it is trained, it's hard to understand why it works, and it's a very, very black box nature. So it's hard to fine tune stuff once it is trained, although it works, right? And how about the multi-scale and long time the behavior? Like some of the simulation has to handle the molecular the scales, the dynamics, or the continuum level, the mesoscale, or maybe your simulations has to handle all these different scales up to the astrophysics scale. And how about not only the space but also the time domains? Your time steps has to goes to really, really small in order to capture very tiny detailed features in very small local regions. Although many other regions you can use the coarser the time mesh. So all these things, is challenging us to build the robust foundation models in computational science. Okay, however, there are like the foundation models available out there, many, many, many of them. Some are very computational, very application specific, many climate models, foundation models for climate exist, and they are advancing this endeavor, uh, although there are challenges. So one of the example is the walrus, which was developed by Polymathic AI, who's the group who made the well repository, like this, trying to make the standardized data sets for the computational science, and they came up with this foundation model to be robust in the cross domains of the PDEs. They did such a good job. And since we have went over some characteristics and definitions for the foundation model in computational science to satisfy, and I asked the ChatGPT and let it run how Walrus works and go over all those examples. They can do demonstrations and the code. And I asked the ChatGPT to, the score those Walrus on the readiness, foundation model readiness of that. And they did they got the pretty good scores for the broad training distributions. They got 0.8. Okay, so the score is from 0 to 1, so closer to 1 is better. Cross-domain generalization is 0.6, reusability 0.5, space-time extrapolation 0.65, data scalability 0.5, scientific consistency 0.3. Yeah, they got the lower score for the scientific consistency because their model is not particularly physics guided. So that's why they got the lower score. Mathematical rigor, their structure is very neural nets oriented and with the advanced neural net architecture. So the mathematical rigor was 0.25. That's why. And um, there's a visual way of representing this the score using this fingerprint like the graph. Um, and you know, it, if it is like more mature in a foundation model sense, then this blue region is going to be closer to the outer, the most circle, and the walrus, based on the ChatGPT, not from me, it got this kind of the fingerprints and pretty doing well on the data distribution and cross domains, but for the scientific consistency, it's not doing well. So I guess as a community, we can use this criteria and try to examine how ready that foundation model is in general in computational science. Okay, so from now on, let me introduce our own foundation models, which is actually inspired by existing foundational methods in computational science, for example, finite element method. So in order to introduce that, I have to briefly explain how the finite element method works. I'm pretty sure you guys are already very familiar with how FEM works, just to for everyone to be on the same page. The finite element method, start with a selecting an element, right? The unstructured element mesh using the tetrahedral. That's very general. So let's choose the tetrahedral. And once you choose the element, you assign a polynomial basis to represent a solutions in any space and time. And a lot of times they use the polynomial basis. And once you chose the basis, you glue them together, assemble them together to form a desirable, complex, the geometric domain. And on that domain, you solve a partial differential equations, and numerically, by solving it, it will give you the unknown coefficient in front of the polynomial basis. Once you find out that coefficients, you can represent any solutions, any time, and any space. These are such a powerful tool, as I said, as a foundational method. It does have a universality and mathematical rigor and software reusability characteristics. And because it's so powerful, even us, like the Lawrence Livermore, a lot of scientists relying on those tools, finite element method, to solve very complex real problem, like the 3D printing process or pole collapse simulations and the 3D shape charge simulations and many others. However, there is a problem with that, and basically they are very expensive. And if you think about why they are expensive, it makes sense because the polynomial basis in finite element method, it does not know anything about the problem, right? Because of that, in order to improve the accuracy, you have to decrease the mesh size, the element size, and it requires finite mesh, or you need to use the higher order polynomials, not the linear, but the quadratic or cubic, in order to improve the expressivity of those basis representations, right? And because of that, by doing it, individual single simulation could take a week on even with the multiple GPU and CPUs in high performance computing, or days or hours, and which is unfortunate because a lot of times we would like to run these simulations multiple times in order to solve a decision-making problems such as design optimization, uncertainty quantification. So we definitely need to do something. And in order to solve the problem, we came up with this data-driven finite element methods because the polynomial basis was the problem. Simply, we replace that with a data-driven basis so that the quality of the basis is improved. And with those improved basis, we follow the same rule, the procedural of the FEM, just assemble them together and then solve the actual physics problem. So therefore, this data-driven finite element method is like tight integration between data driven methods and the physics, the governing equation solving method. And it can be viewed as a hybrid method. So a lot of benefits naturally comes with it. Overcoming many difficulties and challenges I have described before, right? And one of them is the training. So the training becomes very natural. If you think about it, those data-driven bases, you do not have to, generate the data on a large scale, the domains. You only need to generate the data on the small scale, small subdomain, perhaps, which you can do very easily. Like you can even like generate many data, right? And then use compression technique or many other techniques to come up with the basis. So the training and the generating data becomes all of a sudden very easy. And once you get the data-driven basis, the quality is better than the polynomial basis, so you can actually take the larger element size than traditional finite method. That allows us to tackle much larger scale problems. And due to the stability conditions like the CFL, if you can use the larger element size, then you can take larger time steps, meaning implying you can handle, you can simulate longer with a given resources. Okay, let's go over a bit more details of how those, the DD-FEM procedure works, like the training, assembly, and prediction procedure. As I said, you generate broad data set on the small scale, the subdomain level, the size, by solving different types of PDE, Navier-Stokes, Maxwell's equations, and many others. And once your data is generated, you to build the basis. And next slide, I'm going to go over what are the ways of generating those data-driven bases. And once those bases are trained, and you assemble them together, just like the finite method, it could be unstructured mesh by mapping from the reference domain to the computational domain. And then you solve a governing equations, actually solving the physics problems, etc. Okay, and let's go over how we can generate the data-driven basis. One obvious way is using the compression technique. With those big data in the small scale domains, and we can apply the various different types of compression technique like autoencoder or the tensor decompositions or the singular value decompositions or Fourier transforms, etc. You can compress those data and then come up with a compact representations. That's a usual way of getting the data-driven basis. But another way is using the symbolic or sparse regression techniques, where it actually gives you functional forms, just like the polynomial basis in traditional binomial method. And nice thing about this, and you can actually mix those functional forms with the existing traditional binomial method, the polynomial basis, and come up with a hybrid method, the basis. Another way is using the implicit neural representations, which makes the dependency on the mesh, the removed and mesh-free, representations gives you a lot more flexibility, and those can be, of course, used as a data-driven basis. So probably there are many other data-driven basis type, but these are the types we could come up with. Okay, before I show you some of the the numerical results, how the DD-FEM works, let me give you some analogy between the large language models and data-driven finite method. Okay, in natural language processing, the way you train the large language model is you get a lot of text data and sentences and paragraphs and from internet and many other sources. And you break down, right? You break down into the words and tokens, and basically break down into the small pieces. And that's what DD-FEM does. Just like the finite element method, you have a global domain. Complex, how complex it is, it doesn't matter. You break it down into the small pieces, maybe triangular elements or tetrahedral elements, and you do that in DD-FEM as well. And that's basically very analogous to what NLP does. And what does the NLP do after it breaks down? It come up with a vectorized the basis representation for each tokens, and then you glue those pieces together by using some attention mechanisms or reasoning mechanism to come up with a completely new sentences based on what the user provides through the prompt, right? And there's just some mechanism to in this assembly procedure, just like the DD-FEM, right? I mean, once the data-driven basis is trained, and what it does in the assembly, it uses the physics governing equations to actually form a physically consistent the predictions. Just like the large language model use attention and reasoning mechanism, the DT-FEM uses the existing governing equations to derive and guide this global assembly and the solution mechanism. So these LLMs and DD-FEMs, as you can see, has a very tightly similar analogy, and they work together. So maybe it's another way of viewing this DD-FEM can be a very true foundation models in computational science. Okay, let's go over some examples. And to be a foundation models, it's gotta basically be able to demonstrate the generalizability, the capability. Here is the lattice type structure problems where it will demonstrate the extrapolations in space and also generalizations to the inverse problem, not just the forward problem. Okay, this lattice type structure, we came up with these two different types of data-driven elements, the struts and joint. And with those two elements, you can form any type of the lattice structure in 2D, as long as they can be made out of these pre-trained struts and joints. And you apply the external forcing terms and boundary conditions. And with the DD-FEM, because we use the compression basis techniques, the degrees of freedom it had to solve for was 3,872 precisely. But the corresponding traditional finite element method, it has to solve for 2.7 million degrees of freedom. Because of those reduction in degrees of freedom, we were able to obtain a thousands of the speed up with less than 1% relative error. Because it was so fast and accurate, we were able to actually use that to solve an inverse problem, like the design optimization problem, like the minimizing the weights of the overall lattice type structure and get rid of all those blue regions and still hold this external force and boundary conditions without breaking it. And we were able to solve those inverse problem, design optimization problem with 1,000 speedups and with very precise accuracy, less than 1% relative error. And these, data-driven elements, once it is trained, it can be reused without retraining for different types of lattice type structure, right? Let's introduce a lot more struts and joints and come up with a much bigger the lattice type structure, and you can actually solve the inverse problems. Still, you get thousands of speed up and less than 1% relative error. So this DD-FEM is generalizable to much bigger domains. So it enables this natural scale up without the retraining. Well, the examples I gave you was the linear elasticity problem. So there was the linear problem, but how about the nonlinear problem, right? Yes, I mean, it does work for the nonlinear problem. Just to demonstrate that porous media Navier-Stokes, let's try to solve the flow problem with different types of the porous, the obstacles. And in order to realize that, we came up with this data-driven elements, 5 different the obstacle shapes, empty, circle, star shape, and the square and the triangle. And once you train those spaces and then you assemble them together to form this global domain and apply, different inflow and outflow boundary conditions, and we were able to get 25 times speedups and less than 1% relative error. Okay, this one was the steady problem. How about the time-dependent problem? Yes, it works for the time-dependent problem as well. Here is the 2D spatially distributed disturbance Burgers flow, and you trained locally again without any obstacle, just one single element. And then we were able to scale that up for very advection dominated the Burgers flow problem. And we were able to get thousands of the speed up with less than 1% relative error as well. How about the generalizations to different source functions? You probably have pre-trained your data-driven basis with specific source functions like the sinusoidal functions. If you scale that up and try to solve a problem with a much larger scale domain, if you use the same source functions, of course, it works very well, less than 1% relative error. Um, how about like, tweak the global domain and use come up with a different source functions, and it gives you a totally different solution manifold instead of the strips. It gives you the spiral shape of the functions, and it still works with a same single data-driven basis, which was trained with the different types of source functions. So which that demonstrate the generalizations to the different source functions. And how about the generalizations to the different PDE, different the problem? Like to demonstrate that we generate the data by solving Poisson equations and Burgers equations on a smaller scale domains, right? And just to bring the diverse data sets. And then we, of course, solve different PDE types using the same single trained the basis, and it was able to solve the different types of the PDE, Poisson and Burgers, which is elliptic and the hyperbolic. And of course, they can be used to scale things up and etc. Okay, so far I have demonstrated some numerical results, and through those numerical results, I hope you were able to see that we enable the local training and global assembly, make the data-driven training much easier and make it generalizable to many different tasks and problems. And it was cross-domain generalizations, right? And those pre-trained model was being reused once it is trained, and the space-time extrapolation was demonstrated, and the relative error was less than 1%, and accuracy was pretty good because we were actually solving the governing equations, so it was scientifically consistent. And existing mathematical the theory and analysis in finite method or finite volume method, we could take advantage of those and come up with our own DD-FEM analysis. We don't have to start from the scratch. And so I was curious, all those criteria to be a true foundation models in computational science. How does the DD-FEM do? And I asked the ChatGPT again. These are the scores we got. All those criteria, we got pretty good scores. And these are the fingerprint type of the graph. The blue regions was pretty close to the unit, the outermost circle, although it's not perfect. Some of them, like the data scalability, because the demonstration I gave you is we didn't use the broad enough data sets, but we are working on it. I'm pretty sure that could be improved in the future. But I hope that this DD-FEM framework, now you see that great potential to be a true foundation models in computational science. And if you want to know more about like the details, and we made this preprint available for everyone. The title is The Defining Foundation Models in Computational Science. And as Somdata said, I'm leading the Libram team at Lawrence Livermore National Lab. As a team, we try to make a lot of resources available to everyone. Like we have some YouTube tutorials, very short one, 5 to 10 minutes. So you can take a look at them, take advantage of it. And we made a GitHub repository source codes, made it available public, and so that you can generate the solutions and take advantage of this capability yourself. And some documentations through the webpage libram.net, and also the cloud computing. Some of the Libram the softwares are available through AWS, etc. So by acknowledging some funding source, a lot of them are from the DOE, and some of them from the LDRD internal the funding. With that, let me conclude my talk, and thank you for listening. And yeah, if you have any questions, let's talk about that.
Yeah, thank you so much, Yanshu. This was really insightful, very insightful about the foundation models. Before I open the floor for discussion and questions, I would request the audience to introduce themselves before they ask a question. So, just your name and your university or wherever you're tuning in from. That would be excellent to begin the conversation. So, Shovik, do you want to start?
No, no, no. I
Okay.
thought that, yeah.
Okay. Vinayak, you can go ahead.
Hi, thank you, Professor Choi. It was a really nice presentation. Um, can you hear me?
Yeah, hi
Yes.
Vinak.
Hi, I'm from IIT Delhi, a PhD student here. I have a question regarding the strut lattice problem.
Mm-hmm.
In that, I want to know, so the local training that is done in your model is on the strut element and the joint element, right?
Yeah, yeah.
And for that local training, what is the boundary condition that is applied on those struts
Awesome,
and the
awesome questions. Okay, so as you can see, each struts and joint elements are discretized itself, right? So it has a fine mesh within it. And
right?
we apply, random boundary conditions here and here at the end, because those are the interfaces that will, meet with the other elements, right? So in order to take all the possible ways of connecting those struts with the other joints or other struts elements, we randomly generate those boundary conditions, and some polynomial basis sense by changing the coefficients, and that way and you solve on this discretized mesh on each strut subdomain or element, and you solve those the corresponding governing equation, linear elasticities, and generate big data on that. So yeah, that was a great questions, and that's one of the key things you have to figure out, when you train these things.
Yeah. Thank you for the explanation.
Rakesh?
Thank you for the talk. Actually, I wanted to know about the in data-driven model. How do you grade those basis functions?
Oh yeah. So once you generate like the broad data set and big data on, for example, in strut elements, and you use we use the compression technique for this particular lattice type structure. We use the POD basis. Basically, you apply the singular value decompositions and find out the dominant modes and truncate the rest of those. And for like this advection dominated the problems, the POD basis, which is a linear subspace representation, was not enough to come up with a compact representation. So we used the autoencoder neural net type of the compressions to come up with the compact solution representations. So for this advection dominated problem, it required like tens and hundreds of the basis dimensions. With the neural net representation, we were able to get this kind of accuracy less than 1% using 5 or 6, the dimensions. So that's like compression-based data-driven basis generations. But as I explained before, there are many other basis generation methods like this sparse or symbolic regressions or implicit neural representations, etc. But in numerical demonstrations, we use a compression-based data-driven basis generation method.
One more question,
Mm.
like in those while finding the basis functions, so those basis functions like should generalize, right? When we want to continuous learning, like when we want to apply for the different cases, but training for a one case, like for we have trained for the beam problem, and we get the basis functions, but then we want to apply it on some complicated geometries, then would those basis functions be used? Like it should be generalized, right? But how could you generalize those basis functions?
Oh yeah. Well, as I demonstrated here, the same basis functions for these struts and joints were able to solve this type of struts or much bigger type of lattice type structure. And as long as those basis functions which was generated within each element is good enough to represent any solutions within this domain or within these domains, then you do not have to retrain your data-driven basis. But as you make the problem more complex, maybe transitioning from the structural problem to the fluid problem, which holds basically totally different the solution manifold, then you have to go back to the training phase and add those the data, relevant data, which should be able to capture those the fluid dynamic solution manifold, and update those data-driven basis by adding more data. But even that will be pretty fast and efficient because you are dealing with very small scale problem, and fine tuning and those adaptations should be done very efficiently. And we are even thinking about like some sort of adaptive mesh refinement type of strategy here because those training is very efficient. We can probably do so on the fly as you doing the solution process, going through the solution process in the global domain. And just like the adaptive mesh refinement in traditional finite element method, and they do refine some regions on the fly, as the error indicator, some sort of local error indicator tells you, oh, this region is needs more improved basis, and you go back to the training and then improve the basis and then bring the updated basis. Adaptive mesh refinement strategies like that should be applicable to the DD-FEM framework as well. So many tricks and advanced methods which are already used in the traditional finite element method or even finite volume methods, it should be also translated to the DD-FEM framework, and we should be able to come up with those methods as well. So many things to to do and very exciting things to do. So if you are interested, let's work on it together.
Thank you. Thank you for the answer.
Thank you.
Divya?
Hello, Dr. Choi. Thank you for
Hello.
the wonderful talk. I'm Divya, so I'm a PhD student at Johns Hopkins, working with Professor Somdatta. So I
Nice.
had a couple of questions on your presentation. So the first is regarding a very different perspective that you took on foundation models. So you mentioned that the traditional numerical methods like FEM and FDM can be termed as foundation models. So and then later on, you mentioned that, so that is a separate question, but I wanted to know a bit more, like if you care to elaborate on that, why are the numerical methods called foundation models? Because I can imagine that if you change the PD, you need to change the solver a bit. So doesn't that violate the
Uh,
very principle of foundation
yeah.
models?
Yeah. I didn't say they are foundational model. They are foundational methods. It's a method. The method being foundational. As I there are a lot of like for example FEM. There are a lot of FEM codes out there available. Um, like Phoenix is one of them, and at Lawrence Livermore there's a NFEM, and that's another, and many others, right? And those solvers, like the fundamental structure framework, stays the same. You don't have to rewrite the code every single times. You need to you change the problem, like from Navier-Stokes to the Maxwell's equations, or wave equations. You do not have to rewrite those codes, and the reason you don't have to rewrite those code is fundamentals. The framework is the same, like the weak form and discretize things and all that, and that doesn't have to be changed. Only thing you have to provide to those solver is like you have to change the input deck, describing different boundary conditions, and also you have to come up with your own, proper geometry or mesh, and you have to do that. But other things, it doesn't have to change. So that's why it's foundational. And it's not me who came up with those, like the labeling those methods as a foundational in computational science. If you talk to the computational mechanics and numerical folks, out there, um, they will say that those methods are foundational methods. So it is a well-known fact, actually. It's not me claiming the new stuff here.
Right. And
Yes.
when we are defining foundational models,
Hmm.
one of the criteria you mentioned that it should be data driven.
Yes.
Uh, so does that mean that the physics informed architectures do not fall under that, or the way forward is data plus physics?
Data physics inform. Well, I mean, if you are not using the data, if you only using the physics constraint, like pins, physics informed neural network, like depending on how you train them, if you don't use the data, then strictly speaking, since you haven't used the data, right? You only use
Right.
like the residual functional equation forms and try to minimize those objective functions and train the neural net that way, like by solving some optimization problem. Yeah, I don't think that's a data driven. So I don't think that's the foundation models based on our definitions. So it's gotta
Right.
be data driven. Yeah. But I
Okay.
mean, those physics,
And
but those physics-informed neural network or physics-informed neural operator, all those things, they can incorporate the data, and they actually, a lot of people do so. and improve their model. So it could be data-driven.
Right, right. And the last question which I had was you mentioned about learning like a local data-driven basis in the DD-FEM framework. So, so the question which I had was, is the basis changing for every local element?
Bases are changing for every local elements. Okay. So yeah, I mean, as you can see, those element shape can be very flexible. For the lattice type structure, it could be long, rectangular, or ellipse, and any type of the polygon shapes, or it could be square, as simple as that. But some of them, where is it? This type of the elements, it actually has a hole in it, right? The circular hole, the triangular hole, just to represent the obstacle in pole collapse simulations. So if you change the shape or topology of the elements, then yes, I mean, you have to come up with its own data-driven basis tied to each geometric shape of the elements. But if you stick with the square elements, for example, or triangular elements, which is very unstructured, the generalizable elements, if those geometry doesn't change, then actually you can pour many different types of the data onto that same geometric element, which we did in these demonstrations. We pour not only the Burger's equation data, but also the Poisson equation data. And you don't even have to stop there, right? You can generate many other types of the data, very multidimensionals and the multi-scale data into those same subdomain, and then enrich the data sets. And by coming up with a data-driven basis representations, that single basis should be able to handle many different the solution manifolds from different PD types and different problems. So yeah, so it's if the topology of the geometry changes, then yes, you should come up with a different types of the basis. But as long as that element shape is same, then you don't have to come up with a different basis for different PDE. You can just merge everything together and come up with a single data-driven basis to handle many different types of the problem. I hope I answered your questions.
Right. Yeah. That
Okay.
was that was the question. Yeah. Thank you so much.
Thank you.
Wait. Restrict to just one question, Wei, so that because we are already running over time, you can always reach out to Dr. Choi over email.
Yeah.
Okay. Thank you so much. I'm Wei. I just graduated from the Hong Kong Polytechnic University, and I will join Professor Goswami's group as a postdoctor this year. And I am working on the coupling dipole net with the FEM. So I think it's quite similar to your work. I may misunderstand. So in your work, you also have some subdomains that is solved by the dipole net neural operator, and some part of them are some subdomains are solved by the FEM.
Oh, well, that's not what we are doing. That's what SMaRT is doing.
Yeah.
But I totally agree with your connection to a bridge there. The spirit is very, very similar. But as a matter of fact, SMaRT and I are trying to collaborate because of the similarities, and very well being, as I mentioned in this slide, one of the way of coming up with those data-driven bases is implicit neural representations. It could be Fourier neural operator or or a dipole net type of neural operator. And only difference is that I am actually solving the physics governing equations everywhere, even using this neural operator representations. We are not just using neural operator as a pre-trained model and just get the solutions very fast. We just use that as a solution representations. Still, once the neural operator is trained, there is an unknown, like the coefficient in front of the neural operator, which we have to solve for by solving actual physics problems. So there are some difference between your framework and our DD-FEM framework, but I think they can be merged together and in nice way, and come up with a more advanced framework, more advanced method. Yeah, and
Yeah.
in our perspective, I think all of them can be mapped into this generalizable framework. I mean, this DD-FEM, as you can see, it's a framework. It's not a specific method. So I think your method could be mapped into the DD-FEM framework very nicely as well.
Okay. Thank you for your answer.
Thank you.
Arjun?
Hello, am I audible?
Yes.
Yeah. Hi, thank you for the talk today. It was extremely enjoyable. I'm Arjun. I'm a master's student at BITS Pilani currently, and I'm also a research intern under Professor Souvik at IIT Delhi. I just wanted to clarify one thing that I might have missed out because I got disconnected in between, but at the same time, I just wondered if I wanted to know if I've understood the concept properly.
Mhm.
Is the idea of a data driven element, so is the idea that you learn like at a localized level these different kinds of elements and then assemble them, so you sort of have like a generalized parameterized representation of these elements and then you assemble them on a global level to solve it through FEM itself.
Mm-hmm.
So you are basically sort of learning the and then evaluating it at a global level, sort of like
I missed the middle. You said learning the local what? Local representation?
yes. So there was one part in your presentation where you were talking about learning local representations or sort of
Mm-hmm.
localized view of your entire domain, right?
Yeah, exactly.
So is the idea that you learn it at that level and then sort of assemble these
Yeah,
parameterized representations at a more global level?
exactly.
Yeah. Okay. So you sort of have some, say, neural architecture that does this, for example, and then it just evaluates these elements uh, at the appropriate assembled points.
We don't just simply evaluate those trained neural representations in local elements. As I said before, although even though you have trained those neural representations, we use it as a basis, not as a predictor or emulator. Therefore, there's the unknown coefficient in front of those neural representations exists. So to find out those unknown representations in front of those neural representations in each local area, we actually solve a global governing equations, which is described by different partial differential equations on this global domain. So for this particular problem, even after you come up with a data-driven basis on local regions, there is an unknown coefficient in front of it, and we solve for it by solving the linear elasticity problem on this global domain that will give you the the unknown value, unknown coefficients in front of those neural representations. And that way, it becomes a physics consistent because you're actually solving the physics. And also it could be solved very fast because, you are solving for basically very small number of unknowns, and etc. etc. So we are not simply evaluating those trained representations. We actually use that as a basis.
Okay,
Did I answer
yeah.
the question? Yeah.
Yeah, that did answer the question. Yeah, thank you.
Thank
you,
you.
Arjun. I think I would
Yeah,
probably invite Shovik for the last
yeah,
question. Yeah.
yeah. So I'll ask one question, but before that, Sumita did not mention, so I should mention that the Smart Seminar Series, one of the major motivation is your seminar series. So that's how we talked, and I said that let us start something similar. So your seminar
Nice.
series is a big motivation for us to behind starting this, right? So yeah. Anyway, so one small question and then one maybe philosophical question. So one of the in one of the questions, right, you answered that you can learn the basis, let's say for a solid mechanics problem, and then if you go to a fluids problem, you can always retrain it maybe from some data from fluids, right? And the basis function might be needed. I mean, it might be needed that you are updating the basis because the problem of fluid is quite different from the problem of solids.
Mhm.
Now, when you do that, will that, whatever you learn now, will that, if I come back to solid, will it work or will there be catastrophic forgetting?
Yeah. Hopefully it doesn't forget.
Mhm.
That's the that's the idea, and we are relying on those expressivity of those neural net, like you know, universal represent approximation theorem, and all that, the supported by those theory, although it's not that practical. But yes, I mean, that's our hope. I mean, these small demonstrations here, we didn't go through like those fine tuning, like add additional data into the pre-trained model. We just combined all those different types of the data, Burgers and Poisson data, in initial training. But so just to answer your questions, we haven't tried to do so, like pre-trained model and add more data, and does it going to forget the previous data it was trained on? Yeah, but the hope is that, yeah, it doesn't
Yeah,
forget, and because the neural net model is big enough and it can handle the new data in not forgettable way, and so on. That, yeah.
yeah,
I
makes
think it
sense.
depends on how you train them, right?
Yeah,
If you just you know you know just throw away the previous data and then just try to retrain with the only new data only, then there is a possibility of forgetting the previous data, right? But if you
right,
keep those data and then try to integrate both the new data integrate together, then
right.
it'll be more graceful, not forgetting the previous data sets, etc. And then you had another question, right?
Yeah, so that is a more of a philosophical question. So that is like,
Okay.
so in this definition, right, which is quite broad, I will say.
Yeah.
But then there is this also line of work, right, which is domain specific foundation model, or if I, let's say even
Hmm.
weather or climate foundation model.
Yeah.
So
Yeah.
how does that fit this definition? I mean, some of the portion might not, right? The way I see it.
Yeah, probably. Okay, so that's good. Okay, so there are criteria for the foundation model readiness, and those climate model, for example, those foundation model for the climate predictions, like the weather predictions,
Mm.
probably broad training distributions, it'll score pretty well, but
Mm.
not so much on the cross-domain
Right,
generalizations, because
exactly.
it's a very
Same.
application
Yes.
specific, right? It's just
Yes.
for the weather forecasting, it's not for the electromagnetic
Exactly.
simulation. So it's going to get lower score for the cross domains, but the reusability, it will get high score probably, because they are talking about within
Right.
only the weather forecasting, etc.
Mm.
So Space-time extrapolation, probably not so much good score because their domain is kind of fixed. It's a lot of times it's whether it's global or local, it's kind of fixed. So, but the data scalability, they will get higher score, etc. And so, yeah. So I think in that sense, this measure, like the criteria, gives you very fair evaluation criteria. Even though there are foundation models for the climate science specifically, bringing into this criteria, and we can clearly see that what is doing well in some criteria and what is not doing well in other criteria, and characterize those foundation model. We can still call them foundation model, but let's score them, right? Let's evaluate them with.
Yeah. That's fine. I mean, that's why I use the term domain specific. I think that is probably
Exactly.
This is more of a scientific foundation model for PDEs. I mean, that's the way I see it. But yeah, thank you again for the excellent talk. I think everyone enjoyed it, and thank you. So for the audience, we'll have another talk next week. Yeah, sorry, go ahead.
Thank you for the invitations, and I really enjoyed it. And good work of organizing this seminar series. I'm sure you guys will be successful.
Thank you. So much. So for the audience, we have one talk next week, same time, same link. So please join in. Have a nice day. Thank you.
Okay. Thank you.
Thank you so much. Thank you, Youngsoo.
Thank you, Samdata. Thank you.
Thank you.